All right, good evening, good morning, good afternoon, whatever time you're watching this video. This is our day 11 lecture for Math 208 Statistics. For this day 11 lecture, we are now starting in Chapter 4. So we're going to look at sections 4.1 and 4.2 today during this video. We'll also talk about the participation day 11, which is associated with this Chapter 4 material as we get started. There are also some homeworks coming up that are due. So, of course, by all means, do reach out to me. Let me know if you have questions. I'm happy to help. That's what I'm here to do. And then we also are going to be wrapping up our material for test two. So, test two is going to be including all the probability stuff we've talked about in chapter three, this random variable stuff, which we're about to start in chapter four, and then chapter five, where we start talking about some different types of probability distributions that relate directly with the z-score stuff that we talked about back in chapter two, with finding the average, standard deviation, all that kind of stuff from chapter two is going to come back, and it's all going to tie together again in chapter five as we bring the two chapters together where we've been talking about probability, and we're going to tie it back in together with what we saw in chapter two. All right. So test two will be covering chapter three, chapter four, and chapter five, and that'll be done the same way as test one, with this being an online class. All right. So if you have any questions, of course, let me know. Otherwise, for this video, we're gonna go ahead and start in chapter four. All right, so I'm going to go ahead and share my screen here as we look at section 4.1. And what we're interested in here to begin with is first, well, what is a random variable? In essence, if we back up to chapter 2, a random variable is something that we can collect data for. I can collect sample information about it. But there's some randomness in terms of what the outcome will be. For example, going back to chapter two, we were talking about ice cream flavors. Do you like vanilla? Do you like chocolate? What is your favorite ice cream? Using that sample data, I could collect and figure out, well, 60% of the class likes vanilla and 40% of the class likes chocolate. That then gives me probability information about what percent of the class or what portion of the class answers one way or another to that question. But now I could use that information a different way. Say I'm now standing in my classroom and then a random student walks through the door. I'm trying to predict, okay, this random person walking in, do they like chocolate or do they like vanilla? Well, according to the sample data I've collected, 60% of the class likes vanilla, so if a random person walks in, there should be a 60% chance that they will like vanilla. This is the way we're combining what we know from sample or chapter 2, where we can collect samples of data to study a topic or a characteristic about a population, but then we use probability to actually start to try to predict what can happen based off of what we collect in our sample. All right. Now, one issue we kind of run into right away is, well, depending on how large the sample size is, it's not necessarily very easy to create a probability for all the possible outcomes. If I flip a coin, there's only two possible outcomes, right? If I flip a coin twice, well, I could have two heads, two tails, heads and a tails, or tails and a heads. We've done all of that with tree diagramming before in chapter 3. And that's easy enough to create a sample space to write out all the possible outcomes. But we could be dealing with something where what if my sample space is too large that I can't just very easily calculate the probability of each outcome? For example, maybe I want to create a model to predict when will I next be sick? Will I be sick 1 day from now? Will I be sick 2 days from now? Will I be sick 3 days from now? Will it take 10 days before I'm sick? Will it take 20 days before I'm sick? Who knows? On one hand, if I'm lucky, I'll just continue to be healthy and not sick. But of course, eventually, and unfortunately, I'm probably going to be sick at some point in time, regardless of, how healthy I am. Eventually, 100 days from now, 200 days from now, 300 days from now, at some point I'm probably going to be sick, all right? But If I am lucky, that number can keep going up and up and up. Will it take me 400 days before I get sick? Will it take me 500 days before I get sick? If my random variable here is the number of days it takes before I get sick. Well, that could be 1, 2, 3, 4, 5, 6, 7, 8, 9, so on and so forth. It could be any, excuse me, it could be any positive whole number. And so now I have an infinite number of possible outcomes. I mean, assuming I could live forever. Eventually, I'll die, and then, okay, well, I'm not healthy anymore. Um, but otherwise, that number can get really, really big, right? And so this is not something you just easily write out. Well, there's only four outcomes, and if they're all equally likely, then great, we're done. Probability can be a little more complicated than that. So we have this initial problem of, well, how many possible outcomes are possible for some random variable? And like the one I was just explaining, we could have an infinite number of possible outcomes. All right. Consider this example from the textbook. This is example 4.1, where we have a panel of 10 judges who are tasting these wines, and then they are assigning each wine a rating from 0 to 3, right? So each judge has four possible numbers they could assign. They could give it a 0, a 1, a 2, or a 3, right? So we've got four choices. And so each judge of the 10 judges will give a result. And so a single wine will have a rating based off of 10 different judges. So they give this example here where we have 1, 0, 0, 1, 2, 0, 0, 3, 1, 0. Okay. So first, all right, this is a finite set, right? There's only a finite number of possible results here, but it is a very large set. How many possible results could occur here? Well, we've done this diagramming before with different examples in chapter 3. If we take for a moment a marker here. Well, the first judge, he's got four choices, right? He could give it a 0, a 1, a 3, or a 4. Or a 3, sorry. He has four choices: 0, 1, 2, or 3, right? Well, then, in each of those possible futures, the second judge, so after the first judge makes his choice, then the second judge also has four choices. So we see this branching where, well, what if the first judge gave a 0? What if the first judge gave a 1? What if the first judge gave a 3 or a 2, you know? And then the second judge also has four choices, all right? Now this becomes too big for me to draw this entire tree diagram on the screen, but what we do see here was, well, with the first choice, there are four different options. Times for each one of those choices, well, then the second judge also has four choices. Well, then what about the third judge? For each one of those choices, there could be another four choices for the third judge, so on and so forth. And you probably see the pattern here. I've got four choices times four more choices and four more branches, so on and so forth. This happens for all 10 judges. And so we have 4 to the 10th, or in other words, 1,048,576 possible, rating results that could be given. Okay. So it's not an infinite set of possible outcomes, but that's still pretty darn large, right? I mean, I can't easily write out all of these possible outcomes, let alone trying to assign a probability to each one. How likely is it they're going to get one of these out of a million, right? I mean, that doesn't seem very likely. So what can we do? Well, at the end of the day, the way the scoring works, we're told here a score is obtained. So look here in the problem. A score, oops, let me turn off the marker. All right. A score is then obtained by adding together the ratings of the expert. So now this is a little bit easier to narrow down. What are the possible final scores? Well, if all 10 judges give a 0, then the wine gets a 0, right? If all 10 judges give a max score of a 3, well, 3 times 10, that's a max score of a 30, right? So the final score for a given bottle of wine in this competition can range from 0 to 30. Well, now that's much easier to think about. Now I have 31 possible results instead of a million different results. But there is still some nuance here because after all, these different scores, they might have multiple ways it can occur. Now, to get a 0, there's only one way for that to happen. That means all 10 judges gave a 0, right? So only one way for that to happen. But to get a rating of a 1, well, that means one judge gave a 1 and the other 9 gave zeros. Well, did the first judge give a 1 and the others were zeros? Or did the second judge give a 1 and the others were zeros? Or did the third judge give a 1 and the others were zeros? So on and so forth. To get a score of a 1, there's actually 10 different ways for that to happen. And so as a result, well, sure, I have these 31 different scores that can be given, but these different scores might have different likelihoods as they have multiple ways to occur. A score of 1 has many more ways for it to happen than a score of 0. Or take a score of 10. Well, there's a lot of different ways the numbers could add up to 10. We're not going to sit here and write it all out here. But the point is, as we continue in this discussion of probability, we do have to think about a little bit more carefully in terms of, well, how many different ways can something occur in order to try to calculate the probability? All right. Um, Now, before we get too far into that, we do want to discuss then, well, what do we require? If I'm going to create a probability model, what must be true for it to be a functioning probability model? Um, Oh, you know what? Actually, that's going to be in section 4.2. We'll look at that in a moment. What do we need for a probability model? But first, we just want to talk about these random variables. So in the last example, the random variable x, if it was the final score, then x could be any number from 0, 1, 2, so on, up to 30. All right. This is a finite set. There are 31 different numbers that could be given as a final score for some bottle of wine, right? So x is this random variable. Because this is finite, well, we would consider it countable, right? I can count up the total number of possible outcomes. This is called a discrete random variable. So discrete random variables, this is a special case when the random variable is countable. Now, the thing about countable, it doesn't necessarily have to be finite. It could be infinite, but it just has to be listable. I have to be able to, in some way, like count it out or list it all out. So when we say discrete, what we really want to think of is this means that it is possible to list all possible outcomes in some way. And if I do a dot, 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 that's fine. That's a valid way to list it, right? So for example, I was talking about, well, how long would it take me to be sick? Would it take me 1 day before I get sick? So that would be a possible result. Does it take me 1 day before I get sick? Does it take me 2 days? Does it take me 3 days? Does it take me 4 days? Does it take me 5 days? Well, dot, 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 assuming like I live a long life, this X can get bigger and bigger and bigger. And I mean, hypothetically, if I could live longer or live long enough, this number X could stretch on forever if I don't get sick, right? Now, of course, eventually, the probability, the likelihood of me getting sick, my streak should unfortunately end at some point, right? I'm going to get sick eventually. But if with good luck or health or healthy living, whatever you want to call it, it's possible this X could get bigger and bigger and bigger up to infinity. All right. And so even though my random variable, I have an infinite number of possible outcomes, theoretical possible outcomes, it is still considered discrete because I can list it all out. It is countable. 1, 2, 3, 4, so on and so forth. All right. This is a discrete random variable. even though it is not finite. So where do we run into trouble is a continuous random variable. This is not countable. In fact, it's called uncountable. And the most common example here is if we're thinking about, all possible real numbers, right? Um, I could try to predict when am I going to sneeze? Am I going to sneeze in 3 seconds? Am I going to sneeze in 20 seconds? All right. So we can think of this random variable. Let x be the random variable where it equals the number of minutes before I sneeze. All right. Well, the funny thing about this example now, and why it's different from the day example we just did, is that it could be like a fraction of a minute, right? What if I sneeze in 1.5 minutes? What if I sneeze in 1.1 minutes? 1.01, 1.001, right? It could be any possible real number that you can imagine. 1.00000012344, whatever. So now, in terms of what are the possible numbers, well, I could sneeze instantaneously. What if I sneeze right now in this moment as I'm talking? Okay, that's 0, right? 0 minutes have passed. But otherwise, it could be half a minute, 10 seconds, 30 seconds, 22.4 seconds, so on and so forth. It could be any possible real number. Or if I don't sneeze, if I just keep holding it in somehow, or I'm avoiding sneezing in some way, then that number can go on to infinity. But it's different from the past example because it can be any possible fractional number, any possible decimal you can imagine. I can't write that all out, right? I'm sure there's 1.1, 1.2, 1.3, but 1.01, 1.001, 1.0000001. I could spend all night just trying to list out all the zeros for a possible number, and I wouldn't be listing all of the other numbers, right? This is called uncountable. And this is part of what we're getting at here is that there are infinities of different sizes. A countable infinity is like the natural numbers or the whole numbers. 1, 2, 3, 4, 5, so on. You keep counting forever. Well, you're counting towards infinity, but it's a countable infinity. It's a smaller infinity. Whereas the real numbers, the all possible real numbers you can imagine from 0 to positive infinity, that includes all of the decimals. That includes all of the irrational numbers like pi or the number e, so on and so forth, right? There is no way for me to sit here and count all of the possible real numbers. There's no way for me to list it. It's not listable, right? So we have these two different types of infinities. And when it is uncountable, it is not listable. And so this is a continuous random variable, since my only way of representing it is with a continuous number line, as it can be any continuous real number from 0 to infinity. Okay? So we want to make the distinction here because whether I'm dealing with a discrete random variable or whether I'm dealing with a continuous random variable, we're going to have to handle the probability differently for each situation. Now, for this video, we're trying to focus on the discrete random variable case, but as we start chapter 4 here, we just want to highlight what are the types of random variables we can run into so we're aware of them as we come to them later in chapter 4. All right? Now, the textbook here does give some examples to help differentiate between discrete and continuous. The shoe size of a tennis player. Well, shoes generally are only sold in whole numbers or halves. Now, okay, I guess technically you could go to a custom shoe dealer to to take custom measurements to make a custom shoe size. We're not talking about that. We're just talking about like a basic shoe store. Then they're only going to have sizes available in some finite set of numbers, right? That is a discrete random variable where if I'm taking a random shoe, it's going to be one of those fixed possible results for a shoe size, right? There's only a finite number of shoe sizes you're going to see in a shoe store, right? Not talking about a custom shoe store. The number of customers waiting in a restaurant. Do I have zero customers? Do I have one customer? Do I have two customers who are waiting? Do I have three customers? It's possible on some crazy day, maybe I have 10,000 people outside waiting, right? But that is still countable. It is still a discrete random variable because I can list all the outcomes if I had enough time. 0, 1, 2, 3, 4 people, 5 people, 6 people, so on and so forth. I could list them all out if I had enough time. And that's a discrete, countable random variable. Okay. Examples of continuous random variables, the length of time it takes a student to complete a 1 hour exam. The thing here is that because it's like a real number line, it includes all of the possible decimals. Maybe a student finishes in 30 minutes. Maybe they finish in 42.5 minutes. Maybe they finish in 50.000961243 minutes, whatever. Every single possible real number between 0 and 60 is a possible result. So even though it doesn't go off to infinity as a possible outcome, I still have an uncountable, or in other words, this continuous number line of possible results between 0 and 60. All right. So this is a continuous random variable. The amount in ounces of carbonated beverage loaded into a 12-ounce can in a can filling operation. Now, these are filled by machines, right? It's supposed to fill the can to exactly 12 ounces. However, if you've gone to a grocery store, if you look at the glass bottles and the soda selection in a grocery store, some of the bottles, some of them maybe are a little bit more, a little bit less. There's some randomness in terms of what is the machine actually going to put in the bottle. If the machine is working correctly, it's going to give you pretty close 12 ounces exactly, right? But there's some randomness, right? Does it give you a little more than 12 ounces? Does it give you less than 12 ounces? But even here, it's any possible decimal number. Is it 11.9 ounces? Is it 11.5 ounces? Is it 11.42396 ounces? Whatever. Because again, it's like a continuous number line, it's any possible real number. In this case, they're saying from 0 to 12. This is still an uncountable continuous random variable. It is not discrete because I cannot list all of the possible outcomes. There's no way for me to count all the possible outcomes, all the possible real numbers between 0 and 12. All right. So this is the distinction between a discrete random variable and a continuous random variable. All right. Okay. Now let's see. That finishes up section 4.1. So let me clear the screen here. And we now want to look at section 4.2 to conclude this video, where I want to take a moment to focus on discrete random variables. Okay. And we're going to back up to this example that we're familiar with. I flip a coin twice, and what are the possible results, right? We've seen this before in chapter 3. I could have heads, heads, tails, tails, heads, tails, or tails, heads, right? I got these 4 different outcomes. But now let's say I define a random variable. Let x, it's a random variable, where it is the number of heads we observe from flipping a coin twice. Well, then x could be 0, x could be 1, or x could be 2. Okay? But in terms of defining its probability, we have to look at the sample space for the possible outcomes for these 2 coins that are being flipped. Now, we've looked at this from chapter 3. Assuming that they are fair coins, each possible outcome is equally likely. And so for any one of these individual sample points, its probability is 1 out of 4. or in other words, 25%, 1/4, right? The funny thing here, though, is, well, when can x be 0? There's only one way for that to happen. If I have 0 heads, that means I got tails, tails. 25% chance that x will be 0. What about x equaling 1? Well, now there are two ways for that to happen. Did I get heads then tails, or did I get tails and then a heads after that on the second toss? Those are two different possible futures. Did I get a heads on the second toss or did I get heads on the first toss, right? Even though it's the same number of heads, those are different possible futures as they happen in a different order, right? And so when I'm calculating the probability for x to equal 1, well, there's two different ways for that to happen. Add them up together. There are two ways for it to happen out of a total of four possible outcomes, 2 out of 4, or in other words, 1/2. All right. So with this kind of like simple example, we can see all the possible sample points. We assign a value for x based off of the sample points, and then we find probabilities, where in this case, we're assuming each sample point is equally likely. All right. Now, that's not always the case. Sample points are not always equally likely, like if it's a weighted die, or if it's a coin which has been bent in some way so that it favors one side or another, then it might not be equally likely outcomes. But if it's a fair coin, a 50-50 shot, then yeah, it's going to be equally likely for any possible outcome here. All right. Now, based off of this this random variable, we can create a histogram. Recall going back to chapter 2 before we did the probability stuff. This is going back to chapter 1 or back to test 1. A histogram where I represent, in this case, for a random variable, I'm listing the possible outcomes for my random variable. And then the height of my histogram here, instead of a frequency, the height now is representing the probability, which is associated with each value of x. In the same way, frequency, going back to chapter 2, can be used as a way to think of probability. After all, if some result occurs more frequently, then it should have a higher probability, right? I can create a histogram for how many people in the classroom like vanilla ice cream. If 60, or if I have 12 students out of 20 who like vanilla ice cream, well, then sure, on the histogram, I could give them a height of 12, or in terms of a probability distribution, that's 12 out of the 20. Now I can create a fractional or a decimal percentage likelihood probability assigned with that value of x for that random variable. All right. So this histogram stuff we saw back on test 1, this is going to come back to get us here in chapter 4 and chapter 5. All right. So what do we need? I was saying earlier, if we're going to create a probability model, what has to be true in order for that probability model to be functional? Well, first, okay, what is a probability distribution? When we're talking about a discrete random variable, this can be represented with a histogram, a graph, a table, a formula. Look back on this past page. We have the histogram at the bottom, but also at the bottom left of this page, we have table 4.1, where each value of x is listed, and then each probability assigned to each x is also listed. This table is also a probability distribution, right? The histogram also represents the probability distribution. The point of the probability distribution is just to display, whether it's done visually or through a table or through a formula, a probability distribution, all it does is just show us or tell us what is the probability assigned to each possible value of my random variable. In this case, for a discrete random variable. Okay? All right. But now what has to be true for any probability distribution? We have these requirements that are listed here. First, the probability of any value for any random variable, x, it's got to be greater than or equal to 0. right? I'm not going to have a negative probability. I'm not going to say, yeah, the probability of getting heads is negative zero point 0.5. That doesn't make sense, right? We're not going to have negative probabilities. Now, while the textbook doesn't mention it here, it's also worth noting that we're not going to have a probability over 100%, right? Each probability also has to be less than or equal to 1. All right. I'm not going to say, yeah, there is a 150% chance we're going to get a heads when I flip this coin. That doesn't even make sense, right? If it's already 100%, it's already guaranteed. You're not going to have a percentage over 100 when we're talking about probabilities, okay? So, number one here, so it's missing that part, but each probability for any value of x has to be between 0 and 1, right? That's just number one, first requirement for a probability distribution. The second is that if I add up all of my probabilities, and we can go back to this past example that we saw on the last page with the coins. If I go back here and I add up all of my probabilities from the probability distribution, well, it should add up to 1. Why? Well, if I am summing together all of the possible sample points, all of their possible probabilities, well, then that is 100% of what can happen. And if I'm adding up 100% of what can happen, well, then that should add up to 100%, right? Now, 100% as a decimal looks like the number 1, right? We've talked about this before, where decimals and percentages can be represented in these different ways. 100% as in its decimal format is the number 1, all right? And so if you add up all the probabilities, all of them for all of your possible sample points for a discrete random variable, it has to add up to 1. All right, so we have these two requirements here. So let me go back now to the page we were looking at. So all the probabilities, they have to be between 0 and 1 for each individual probability. And then if I add up, if I sum, this is our sum notation here, where we have this capital Greek letter sigma. If I add up, if I sum up all of the possible probabilities, that has to add up to 1. All right. So long as these two things are followed, then it is a valid possible probability distribution. If one of these things is not followed, or if it's broken, then it's not a valid probability distribution, okay? So you'll see things popping up in the homework asking about this, or using this to try to figure out some unknown values given some probability distribution, okay? Now to wrap up here, I'd like to look at this drought problem. This is example 4.6, and I'm also going to do this on the whiteboard behind me, so let me turn off the screen share. All right. So this is example 4.6 from the textbook, where we are told a drought is a period of abnormal dry weather that causes serious problems in some farming industry. Okay. The University of Arizona researchers used historical annual data to study the severity of droughts in Texas. These researchers, they create a distribution based off of the historical data where X is the number of years before a drought occurs. Or rather, it is the number of consecutive years that have to be observed before a drought occurs. All right. So until a drought year is observed. So X, our random variable, is the number of years before a drought occurs. All right. So this is a discrete random variable, and in fact, this is like the sick example I mentioned earlier. Will it happen after 1 year? Will it happen after 2 years? Will it happen after 3 years? Will it happen after 4 years? So on and so forth. Now, if they're lucky, it may just go on and on and on without a drought occurring. Maybe it happens right away. Okay, that would suck. That'd be bad luck. But maybe it just keeps taking longer and longer before a drought occurs, right? Who knows? Maybe it takes 5, 6, 7, 8 years, so on and so forth. If they're lucky, this number could go bigger and bigger and bigger. It's possible. And so we have this kind of discrete random variable at play. All right. Now, from the data they've collected, they are able to create a formula which says, all right, well, the probability that it's going to occur for some x or after some x is zero point 0.3 times zero point 0.7 raised to the x minus 1. All right. And oh, actually, they have here that x can't be 0. So it doesn't happen right away because, well, it's the number of years that they have to sample first before it occurs. All right. So it has to be at bare minimum 1 year, and then it happens. Or 2 years, and it happens, so on and so forth. All right. This is the formula they create. Now we could ask the question, find the probability that exactly 3 years must be observed before a drought occurs. So this would be find x is 3, in which case the hard work in this case has already been done for us. We already have the probability model. Now, in later sections of this textbook, we'll talk about how to create the probability model ourselves. But for now, as we start chapter 4, they give us the probability model. So all that's left for us now is just to plug it in and see what happens. So P of 3 will equal 0.3 times 0.7 raised to the, this will be 3 minus 1, which is 2. So it'll be raised to the second power. Now we go to a calculator, carefully type it in. I'm going to have 0.3 times 0.7 raised to the second power. And I am getting an answer here of 0.147. 0.147. All right. Now this is a decimal, right? I could rewrite it as a percentage, but I have to move the decimal point twice. 0.147, or in other words, if this is out of 1, right, then this is 14.7%. Okay? So there's about a 14-15% chance that they're going to have 3 good years and then a drought will occur. Okay. Well, we got that. I mean, we could plug in different x's and see what happens. But the point here is just that this model allows us to have this kind of prediction for the future at play. Now, how good is this prediction? I mean, we'll see, right? I mean, unfortunately, in the world of probability, in the world of statistics, this is just an educated guess, right? It's no guarantee. It's just a guess. All right. Now, we're also going to use this formula for today's participation question. So if you go and look at participation day 11, and I'll switch back to the screen here. Let me share my screen again. All right. Participation day 11, we're given the same random variable and the same formula. Now we're asked, well, find the probability it will take 2 years before a drought will occur. Okay, well, then we go to the formula and we plug it in. P of 2 is equal to 0.3 times 0.7 raised to the, so I'm, oops, use a parenthesis, raised to the, I'm using the upper caret symbol for an exponent for a power, just for typing on the screen, but on a calculator, I would use the power button, all right? 0.7 raised to the 2 minus 1. Well, 2 minus 1 is just 1, so that's nice. That's just the first power. First power. So my answer is 0.3 times 0.7. And we find out then the odds that it will happen after 2 years is 0.3 times 0.7 is 0.21. All right, so unfortunately, it looks like, and I believe this was in Arizona, this model was done, where I mean, because of that being a drier region, they're going to have droughts more frequently. So it becomes less likely for X to be a high number. It's more likely for X to be a small number, which is what we see here. When X is 2, now the likelihood is 21%. Um, so on and so forth. All right. So 0.21, that is our answer for today. Or if you want to write it as percentage, that is 21%. And we have our answer for participation day 11. All right. That will wrap up our material for the day 11 lectures. We are wrapping up chapter 4 for sections 4.1 and 4.2. In the day 12 material, we will continue into chapter 4, but for now, we'll stop there. If you have any questions, feel free to email me, come by office hours. Otherwise, best of luck, and I will see you all in the next video. All right, have a great day.